Record. Did I hit record twice? Okay, good. So let's dive in. Today is forces, dynamics, and I'm going to start from the beginning in the possibility that your minds have completely blanked. There was a midterm, immediately after midterm brain reset. No shame. I'm not shaming anybody that happens to. It certainly happened to me enough in my undergraduate. Hopefully, you retain and compactify your understanding. Your understanding grows with each passing week. But in practice, after the stress of the exam, stuff gets forgotten. So let's review briefly. I'm going to start from the beginning. Dynamics is the study of forces, and I start by intuitively, very straightforwardly defining. A force is a push or a pull, and it makes a very big difference if I push something to the right than if I push it to the left. So forces are vector quantities. In particular, we're going to link force with acceleration in Newton's second law. And it maybe shouldn't be a big surprise that if I push something to the right, it accelerates to the right. If I push it to the left, it probably accelerates to the left. And so the direction of force can be positive or negative. And that's very important. Negative forces and positive forces, the sign matters. Okay, force, the unit here is the Newton. 1 Newton is how much resultant, total, net, unbalanced force, lots of ways of saying same thing, required to accelerate a 1 kilogram mass at 1 meter per second squared. I want to emphasize the unit, the Newton, is equivalent to 1 kilogram times 1 meter per second squared, 1 kilogram meters per second squared. But whenever we're talking about M and A, we would say kilogram meter per second squared. Whenever we're talking about F's forces, we're going to talk about newtons. So there might be an equivalent, but that doesn't mean you use the same thing. For instance, I am Dr. Tucker. My wife calls me Ross. Those refer to the same person, but in different contexts, they're applied differently, right? Don't call me Ross. And it's weird as all get out if she called me Dr. Tucker. That'd be like, I don't know, relationship counseling there. Here's something new. Well, sort of. You already have been introduced to a lot of weight in last week's lab. Those of you in the lab section have heard a fair amount about friction. And I talked briefly about normal force. Let's go into these in a bit more detail. This is still an introduction, except for weight. The other 4 models we're going to go into exquisite, excruciating detail later. But one step at a time. Weight force, God willing, you know a fair bit about. Gravity acts on an object, exerts a downward force of magnitude mg. Bam, that's it. You will always and only ever use weight when there's a planet nearby, which is most of the time. I should emphasize one thing I should have put on this slide is weight force always applies if you care about the vertical direction. You know, if I'm just walking back and forth, accelerating horizontally, I don't care about weight force because I'm not moving up and down. I don't care about the up and down motion. I don't care about acceleration. There's a normal force balancing my weight force. The floor is supporting my pull downward. I don't care about that. Well, if I start jumping up and down in the air, then I do care about vertical forces. I would write both horizontal and vertical. Okay. Weight is the only long-ranged force. Every other force involves contact. That might seem simple enough, but this is a big cause of goof. Being able simply to think about a scenario, envision a scenario, look at a scenario, and identify what is acting on what is huge. Very, very easy to make mistakes. I'm going to give you a process to help you avoid that in a second, but I want you to think about this. It must touch to exert a force unless it's planet, unless it's exerting a weight force. Okay, so the 4 touch forces that we're going to spend the vast majority of our time with are called normal, friction, tension, and spring. Normal is when 2 solids touch. Friction is also when 2 solids touch. Well, actually, all of them are solids, but normal, I'm going to focus on 2 solid objects, a book sitting on a hand or a table or whatever, 2 solid objects, and the normal force is the force which is exerted at right angles to the surface. If the surfaces are horizontal, normal force is vertical, either up or down. If I push on this wall, Well, the wall is vertical. So I'm exerting a normal force here. My hand is solid, so is the whiteboard. It is pushing out of itself, exerting an outward normal force, a horizontal normal from a vertical wall. Huh? Normal force is very common, but normal does not mean always. Normal does not mean everyday. Normal does not mean typical. Normal means right angles. Friction is parallel to the boundary between two surfaces, the interface. So if I've got a friction force on a vertical wall, I'm moving my hand up and down. The normal part of the contact is the wall is pushing out on me horizontally, keeping my hand from just phasing through the wall. And the vertical part of the force that's exerting on me is trying to prevent my hand from going up and down as much. Yeah, bigger the friction force, the harder it's pushing on my hand, the harder I have to push back. That's in this case, vertical surface, vertical force. I'm going to say, there's another thing that I should add to this. When two surfaces are tending to slide over one another, that can mean when two surfaces are, or when two surfaces are trying to. Tending is perhaps too subtle a word here. Tending does not mean they have to be in relative motion. So far, so good? Okay. Tension and spring force are the only two absolutely new ones here. They're both ropes. If you've got a rope, a cord, a string, a chain, a long, skinny, twisty, not twisty, a long, skinny, flexible thing. It can pull, okay? Either use a tension or a spring model, and here's the difference between them. If the thing is really stretchy, use the spring. If you care about how far it stretches, use the spring. If it doesn't stretch that much, or you don't care about the stretch, use the tension. It's not that one is correct and the other one is incorrect. You could always apply a spring model. You could use the equations for springs, but just like in our kinematics lessons, where if you've got the initial and final velocities, you don't need to calculate acceleration. You can do it another way. There's a simpler equation to use. Average velocity times time gives you displacement. Remember that? You can solve for stuff that isn't important. So if I don't care about the stretchiness of the material, don't care about how much it pulls on the string, then who cares? Just model it as a tension. We're going to give you characteristics, techniques, some equations to analyze each of these scenarios. But the big difference between tension and spring is just, do I care about the stretch? Everything stretches somewhat. There is no unstretchable material. Not that I know of, anyway. It's just some stretch a couple of molecule lengths and some stretch like a slinky is very easy to stretch. Questions on tension versus spring force. It's got like 5 people ask me questions in the 3 o'clock. Did I do a better job of explaining it now? And again, we're going to give details on all of this, but for now, yeah, ask. Tension, spring force, or do they kind of work together? It's a matter of you wouldn't do both. You wouldn't count something as both. There is one interaction. If I pull on a cord and I want to know what happens, well, depending on whether the cord is very stretchy, is significantly stretchy, is stretchy to the degree that I care about that precision, I might analyze it using the equations we'll discuss for spring force. Or I might just say, I'm hanging on a rope. What force does it exert on me? That'll be the first problem we do today. I don't care if it stretches or not. I would use the tension ideas that we're going to develop. For now, I'll say we're going to talk about springs rather in detail later. But for now, I'm going to have everything be these first 3 contact forces. Tension is going to be a force exerted by a rope. And I say put rope in quotes because, you know, anything long and stretchy and long and bendy can be a tension. Anything long and turny. Does that answer your question? Other questions? Particularly about the difference between these two. How about the difference between friction and normal? Feel better with that? I had like 2 questions in the 3 o'clock. Yeah, question. Okay, so when I say tending to, I don't mean that they have to be sliding. They are either sliding or they want to be sliding. They're trying to slide or succeeding at sliding. There is either relative motion or there is a push trying to get relative motion. Okay? Good? I always do that. Let's recap Newton's laws real fast and then move on to some methods. 2 methods, right? Okay, first off, and then examples. The rest of the class is examples. First off, Newton's laws. If and only if an object is not accelerating, if velocity is constant, then forces are in balance. If forces are in balance, then an object's velocity must be constant, no acceleration. I say this, in other words, as inertia is a thing. Everything has inertia. Things try to keep moving or stay at rest as they were. And if they are, then there are no unbalanced forces. Well, what if there are unbalanced forces? Unbalanced forces, total forces, net resultant forces, all the same thing in different words. Total force causes an acceleration. I want to emphasize here, by the way, vectors, the direction of the force is the same as the direction of the acceleration. If force is up, so is acceleration. If force is down, so is acceleration. You can find the direction of the total force by looking which direction the object is accelerating. That shouldn't be super mysterious. But 3/4 of the 3 o'clock class struggled to remember that when we were doing a problem. Think about it for a second. Try to internalize it. If you know that something is accelerating upward, which direction force must be winning? The upward force. If something is accelerating downward, which direction force must be winning? Downward force. Yeah, good. So far, so good? Now the concept that most wrecked people, other than the first 2 questions, the biggest force concept that wrecked people on Wednesday last week was Newton's third law, and in class too, what I was saying 2 weeks ago. Third law says if A pushes B, B pushes A, and I want to be precise, the amount of push is the same, the direction of push is the opposite. The big goof here is people introduce 3 objects into it. If the table supports the water bottle and the earth pulls on the water bottle, those aren't third law pairs. That isn't action and reaction. The table supports the water bottle pushes the table. That's a third law pair. The earth pulls the water bottle pulls the earth. That's a third law pair. You have pairs of forces, 2 forces. You have 2 objects interacting, table and water bottle and table, earth and water bottle and earth, A and B, B and A. You never introduce a third object into Newton's third law. We will spend a significant amount of time, at least a whole lecture, doing nothing but example problems to master the third law. Not today, though. Not today, Satan. You're not Satan. Physics is Satan. Let's give a technique here to identify forces. Please follow along. This may sound stupid. Trust me, it'll help. Missing a force or giving an extra force to an object is so freaking common. I cannot even tell you. There are 100 people in this room. I guarantee there will be at least 200 missed or extra forces over the next week in various problems you do. Everyone makes this mistake at least a couple of times. So here's how to avoid it. 1, to identify forces. 1, is there a star or planet nearby? Do I care about the vertical direction? If so, weight. Weight acts down. You've got an equation for his strength. Bam, that's it. Done. Bazinga. To get every other force is a contact force, remember. I'm going to draw a sketch. Doesn't have to be artistic, doesn't have to be fancy. I'm going to draw a bubble around the object that I want to analyze, object or objects, whatever your system is, whatever you care about understanding, draw a bubble around that. To exert a force on that system, you must cross the line. You're crossing the line. If you want to exert a force on the object, that object must be in contact with. Then you consider the dictionary. Normal, friction, tension, spring. For now, there are just 4 kinds of forces. That's it. That's it. You have to consult the dictionary and identify the kind or kinds of force. Yeah. The sketch includes multiple things. For instance, if I were sketching this scenario, I would draw a table surface. I would draw a water bottle. I would draw a dotted line around the water bottle. Hey, the table is going through my dotted line. If an object passes through the dotted line that is drawn around the object, that object is in contact with, that object might exert a force on. I'll do examples in 2 seconds. You'll see more of that. Other questions? Okay, let's do an example. This is not the only sketch you'll draw. I'm going to show you in a second. Once you do, oh, for God's sake, what am I trying to say? Once you do a physical sketch, I'm going to have you transform that into a free body diagram sketch, a force sketch, and then turn that into Newton's second law. It's a very step-by-step process, but it starts by identifying the forces. Okay, here we go. Buckle up, baby. Start by simply sketching and identifying what acts on the gymnast. Google question A, just identify what acts on the gymnast. You could talk to your neighbor. You should talk to your neighbor. Draw a little sketch. Do it. Don't skip it. Until you're really good at this, always do it. Huh? Don't answer the question yet. I'm going to build you up step by step. A whole bunch of people tried to do it immediately. Do it in one step, and 2/3 of them got it wrong in the 3 o'clock. Let's build it up. What forces act on the object? That's all I want you to tell me. One more time. Google question A, simply identify what forces are acting on them. Use the process. External forces is correct. I want you to name them. All right, let's go through this. There is a planet nearby every the acrobatics competition. What do I say? Gymnastics competition I've ever seen has been on Earth, at least. So I'm going to include a weight force. I care about vertical direction, bam, weight. Also called gravity, but I would strongly suggest we use the same word for it. Weight force is acting on the gymnast. What is touching the gymnast? What kind of forces do ropes exert? Bam, that's it, weight and tension. If you said normal, I challenge you to show me the solid surface that the sucker is attaching to. If you included 3 forces, I challenge you to show me, besides gravity, the 2 different objects that are pushing or pulling on her, him, whatever. Yeah.
So the weight force is acting on the gymnast.
Yes.
Tension is applied by the gymnast on the rope.
Well, by Newton's third law, that's true, but I don't care about the rope. I care about the gymnast. If the gymnast pulls the rope has to pull the gymnast.
So the tension will be on the.
If I care about the gymnast, tell me about the forces on the gymnast. There's a rope interacting with them, exerting a tension force up. Yes, please, Jane. Well, it is solid, but all these different forces, fundamentally, all the contact forces are actually, in truth, part of the electroweak force. Ultimately, all of them are electrical interactions. Which one of those 4 you use is a model of student's choice based on what it makes sense to use if you know enough about the hand squeezing and the materials interacting. You could do a friction model. But I'm going to start you by saying if there's a rope, just call it a tension and be done with. I didn't give you enough to know about friction or enough to know about springiness. At the end of the day, all of these are models. They are simplified ways of representing deeper truths. Other questions? This doesn't get simpler or only add complexity. So if there's something you're missing, ask before it gets harder. Yeah, please. I'm saying that the rope could exert a friction force or a tension force or a spring force, depending on what you know, depending on what you care about modeling. Do you guys know what I mean by model? A model is a simplified representation of something. In physics, we say no model is true, some model is accurate, some model is useful. So when I give you an idea about weight equals negative mg, Newton actually discovered more than just that law. We might discuss that in module 3. Einstein discovered lots more about the nature of weight force, and Einstein's model is so insignificantly different from mg for our purposes, who gives a crap? But you do want to go deeper into the true nature of things. Nobody has ever measured anything that has disagreed with Einstein's law of gravitation. No one has ever found experimental evidence that Einstein was not exactly right. Nevertheless, in physics, we do not have axioms, we do not have proof, we do not have theorems, we have laws, and a law is a statement, a model, an idea which is true until experimental evidence shows otherwise. That's the scientific method, baby. That's the essence of science. So when I say model, I mean we are using a way of analyzing something, an equation, a set of equations that represents something. And which model do you use? Well, none of them are completely the universe itself, but some of them are useful. Pick one and use it. Right now, you don't have enough information to deal with this as friction. You don't have enough information to deal with this as spring. And I use the word tension in the problem statement, so we're going to call it a tension force. Yeah? Does that answer the question? More or less? Okay. Okay, so you have analyzed the nature of the forces. There are 2 forces, weight down, weight down, tension up. And now we're going to write down the net force equation. Here's how to find the net force on an object. You add all of the forces up together. Ups are plus, Downs are minuses. So if I add a negative, that's the same thing as subtracting its magnitude, right? Net force on this object equals, add all the forces together, there's an upward tension, and weight is downward, so I could call it minus W. W here is not the vector. Vector already points down with the magnitude. I could simplify this to saying T minus W. That's the net force. And then what, by Newton's second law, is net force equal to? In this case, mass times 0. Why 0? Just hanging there. Okay, so first step, identify the forces. Second step, ultimately we're going to write down Newton's law. What are the forces? Turns into the F net, the left side. What is the right side? Well, in this case, it's darn simple. Can identify. It's not accelerating at all. It's just hanging there. A is 0. At the end of the day, we plug in our equation or equations that we have learned to represent things in this problem. Do I have an equation for T? No, only coffee. Only weight. Tension minus mg equals 0. Plug in numbers. Tension, solve for tension. Tension equals approximately 540 newtons. Bam. Turn to your neighbor and express the steps I just said. One more time. Here's my version that you should put in your own words. Identify the forces with the aid of a diagram. Write down Newton's law, F equals ma. Apply equations, solve for what you care about. Okay, turn to your neighbor and tell them that, and then we'll do another example. Then we'll do another example. Then we'll do another example. Can I explain why W what? Well, I say the weight force acts downward with magnitude mg. If I am adding together all of the forces, weight acts downward, negative direction. If I just say W vector, I will plug in a negative sign, but if I say that there's a negative negative, that would have mg pointing upward. No, that doesn't make sense. You must include one and only negative sign, one and only one negative sign, when adding together vectors. If that vector's down. Yeah. mg. 55 times 9.8, and I round to 2 sig figs. If you got 539, 540, same diff. I'm not an accountant. Significant figures are not a skill that I'm teaching in this class. So if you get an answer that is very close to mine but has more decimal places, you got it right, okay? I will never ever give you something where the correct answer, the standard physics answer, and what you get out of your calculator are significantly different. Significantly figurally different. Does that make, yeah? Yeah? Other questions? Okay, let's make it harder. Ready? No? Questions? You are good. Work with your neighbor. What is this? B, is this B? See if you can do the whole thing. It's a very similar situation. I want you to see if you can solve it all. Why is there no coffee? What do we measure forces in? Don't tell me kilograms. Correct answer is not in kilograms. No is not correct, by the way. If you're confused, go back to what we just did. What does each letter mean? What is each step? One little step at a time, just a little bit. And that's half of you. Correct. More than half of you. Yeah, someone fixed their wrong. Correct answer is exact same as the previous. Exactly the same as the previous. None of the force natures are different. There's still a tension up. Half a second. There's still a tension up. There's still a weight force down. The only thing that changes is we are in steady motion, but steady motion, that's not accelerating. That's not accelerating at all. If I give you, they're moving at a constant speed, moving upward at constant speed, bam, yeah. Yes. I can't hear. You need to shout, please. I am old and decrepit and I cannot hear well in this background. What do you get? No, I'm just, what did you get? Oh, okay. So do you agree that tension minus mass times field is 0? Did you get this far? Is this? You sure? If you didn't get up to this step, then ask earlier. No, I don't think you like this. Tell me where I lost you. Times. Yep. Okay, so tension plus negative weight is the same thing as T minus W, right? If I add a negative, yes. Now, what's Newton's second law say? Net force equals This is the central equation of all of dynamics. Memorize this sucker immediately. Net force is mass times acceleration. Net force is mass times acceleration. What's the acceleration here? Zero. Why? How do you know? Yeah, exactly. Just hang in there motionless. So any number times zero is what? Right. What is the weight formula? M times G. So instead of writing W, I wrote mg. Instead of writing m times zero, I wrote zero. Okay for this line now? For realsies? Great. So I plug in a value for m, I plug in for a value for g. What's m? What does that mean? In this case, it's 55. I told you she's 55 kilos. So m is 55. What's g? Gravitational field of Earth. Assume she's on Earth. Great. T minus 540 equals 0. T equals 540. Sure, absolutely. Other questions on either part? Yeah. You tell me. What's the acceleration if you're moving at a constant speed? You've answered your own question. Acceleration is 0. You don't add velocities. If you're climbing up a rope, you are climbing constant speed and constant direction. So velocity is speed plus direction. And if I'm telling you you are climbing up the rope, climbing at constant speed, we're presumably not going in a circle. Yes, so please note, please note, please note, Newton's first law still applies here. We're moving at a steady motion, no acceleration. Forces are balanced if you find the weight force that's equal to the tension force. This will be a quiz question and a midterm question, and probably a final question. I will ask you something where you can analyze it and recognize, oh wait, net force has to be 0, constant velocity, no acceleration. Straight line, no change in speed. Do you see? Do you see? Do you see? For realsies? For realsies, if you have further questions, for the love of Newton, ask. Okay, let's do the next example. Same forces, but I'm going to change another thing. Can use the previous analysis, except one more thing changes. See if you can figure it out. Give it a shot. A lot of correct answers. People are learning something. Oh boy. I love it when people learn things. Two minutes. Oh my God, more than half of you have got this right. At this point, that's good.
Advice you told me to do for your class exam, I did it in another class and I missed it this time.
Huh?
Remember how you said when I were talking about the sales exam, I missed the class? I just did that with another class. I think that's the you had, right? This class failed. Because this could really be another, it's the same exact thing.
And wait, put in your best shot. Or, you can ask me a question in here. If you're shy and do not want to raise your hand, you can ask me a question in here. Tell me where you're lost. Or you can ask a question out loud. I like those too. Question me.
I'm using T minus mg equals a. Okay.
E minus mg is your total force. Newton's second law does not see net force equals acceleration. What does? Can you state Newton's second law equation? Yeah. You wrote F, but you wrote MA. You just wrote A instead of MA.
Like first slide did, it was P minus weight equals M times A on one side, and then it went down to T I think minus mg 0.
If I know that A is 0, no, it's mass times acceleration. Whatever mass is, mass times 0 is still 0. I don't need to write m times 0. That's silly. Anything times 0 is 0. It's not that the m went away. It's anything, mass times, any mass times 0 is still 0. Good question. Let me do a final count. There's my final count. You get an A. And that is, oh my sweet baby Newton. I'm so proud of you all. 77 people got this right. Good. 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 Okay. La respuesta correcta. The correct answer is 610 newtons. And here's how to analyze it. The forces have not changed. The nature and direction of the forces have not changed. Left-hand side is still tension, up, weight down, T minus mg. But now the right-hand side is not 0. Acceleration isn't 0 anymore. I can plug in. You missed what? Ask me.
Is it MA?
Is what MA?
Mass
Stop saying it. Is what MA? This is Newton's second law. Total force, mass times acceleration. That's always true. Other questions? Give me more questions. Tell me where you're lost. Tell me what's troubling you. Show me your hearts. Not literally. I'm not that kind of doctor. So the weight force is downward with magnitude mg. Don't double count the downward. You can't double count the downward. If you've got the total force, add all of the forces, downward ones get negatives because they're downward. Don't include a minus negative mg, otherwise you'll be adding to upwards. That's double counting. Other questions? Any questions? Questions on my math? Okay. Oh, wait. MG. How about a conceptual one? Here we go. Google question. Oh my God, are we only to C? I usually torture you guys a lot more than just 3 questions so far. Okay, still, here. Here's D. Just answer 1, 2, or 3. Question in the Google form. Is net force the same as tension force? No, almost never. Net force means take all the forces in some direction, in the direction you care about, and add them together. In the previous example, tension was one of the forces that acted vertically. Actually, in this example too, there's an upward tension force, but there are 2 forces, so tension and weight together make up the net force. Tension is not the same thing as net. Net means everything added together. Yeah. You tell me, what does it make sense to do in this problem? What is the net force? What is the acceleration? You don't need to do anything different. You do the same steps as before, except in this case, I'm not asking for numbers. Just look at directions. But you could do exactly the same steps as before. Write down the same equations. Reason about the same directions. Oh dear God, you're getting it right. You're getting it right. You're getting it right. Do a little professor dance. Do a little professor dance. I don't know about other faculty, but like when I see green on my Google form, it's like a hit of cocaine, baby. That's what keeps me coming back. Yeah, give your professor another hit. Give me those sweet right answers, man. Come on, I need your right answers.
Last time I got a 90% on an exam, I did a dance.
You did a dance? Yeah. Well, I do dances when I grade them too. See people do good grades. Okay, so we're going to analyze this. We don't got numbers, but we don't need numbers. All I'm going to do is recognize the forces here are the same as the forces before. Net force equals ma. Bam! Now, let's talk directions. Tension up, weight down. I've already included the signs by having a minus, yeah? Which direction is it accelerating? Wait, let me check that, see your kinematics. If your kinematics are bad, then that'll screw everything else up. Real fast. Up, down, 0. Question E. Which direction is acceleration? Up, down, or 0? Google question E, based on what I've asked, is acceleration up, down, or 0? Yes. Ooh, okay, so people either didn't learn or have forgotten what acceleration is. Ooh, that's about 50% right. Ouch. Read carefully, my dudes. Change one word in this and it'll be different. And please talk to each other. Talk to each other, help each other out. Moving downward, slowing downward. Moving downward and slowing down. How do you find the direction of acceleration if you know moving downward and slowing down? Talk to each other, help each other. A lot of wrong go answers here. Better. Still not what I want it to be. Okay, here's one way to analyze this. Draw a velocity time graph. Let's suppose, just for the hell of it, that at some time the velocity is negative 25 meters per second. That's a downward velocity. I told you it's moving downward. Now, if it slows down, tell me a slower downward velocity. Negative 10, negative 20. It's a negative because it's moving downward, but it's closer to stopped, which is 0. Wow, that's not to scale. Well, that looks stupid too, but okay, great. So at some time 0, I'm moving at negative 25 meters per second. At some later time, I'm moving at negative 20 meters per second. Now here's the question. Has my velocity gone up or down? Wait, Google form, is this an increase or decrease? Question F, has my velocity increased or decreased? Have I added to or subtracted from my velocity? Nope. Okay, again, 50% here. Okay. A number increases if I add to it. A number decreases if I subtract from it. Number increases if it goes up a number line or to the right on a number line. Number decreases if it goes down or to the left on a number line, depending on how you draw the number line. Okay? From negative 25 to negative 20, have I gone up the number line or down the number line? Do I add to or subtract from negative 25 to get to negative 20? Are you sure? Only like 5 people answer that. Okay, Google form G. Do I need to subtract or add to negative 25 in order to get to negative 20? I want to make sure that everybody agrees on this. Add or subtract? What do I do to negative 25 to get to negative 20? Okay, only about 5 people answer, but it looks like most people agree. Most people agree. The correct answer is negative 25 plus 5 equals negative 20. So again, if I have negative 25, and if I subtracted 5, what would I get to? I get to negative 30. I'd have to go negative 25 plus 5 in order to get to negative 20. This is up the number line. This is an increase. I add to, I am increasing the number. That's it. So which direction is my change in velocity? Upward. Which direction is my acceleration? Okay, Google question H. I have led you up to the stream. Now drink for me, baby. Which direction is the object accelerating, positive or negative? Google form H. Everything that I've been doing leads you to this. Is acceleration positive or negative? You don't know it's constant, but you do know the sign. Again, please consider what we just said. The change in velocity to get from a negative number to a less negative number, we add to. Delta V is plus. So delta V divided by delta T is also plus. If I divide by time, time marches forward, baby. Time does not go backward, not even if you go back to the future. Unless you're going at exactly 88 miles per hour in the imaginary direction. Okay, correct answer is acceleration is positive. So tell me, acceleration times mass is positive or negative? Nobody's ever observed negative kilograms. Correct answer is positive. So tension minus weight is a positive number. Which wins? Which is bigger, the plus or the minus, if it combines to make a plus? Correct answer is, I've led you up to the water. Now drink for me. Google question I. Give another stab at the correct answer. I have led you up to here. Tension minus weight is a positive number. Fill in the blank. Please write just the number 1, 2, or 3. Okay, I'm going to call times up. There are a whole bunch of people that have either stopped answering or logged in and fell asleep or something. There are a lot of no answers in here. Let me remind you, if you're not participating, I'm going to kill your participation points. Just your name is not enough. Also, stop Gmailing. Oh my God. Just said this. The correct answer, if T minus W is a positive number, the positive one of those must be bigger. Tension is bigger. T is bigger than weight. Correct answer is 3. Question me.
You know how in the previous question the acceleration was 1.3 meters per second square?
It is in the previous one.
Yeah. You can check my
Sure. Tension was 610, weight was negative 540. Yeah.
calculation.
Sure.
611.
And to 2 sig figs, that is 610. Go on.
This, what I did was since the
But you were assuming the acceleration is downward. You assume the acceleration is downward, acceleration is upward.
Yeah. So according to like the things which you just taught,
Mhm.
I'm correct.
Mhm.
My question is this: if the velocity is decreasing, the acceleration will always be in the opposite.
If the speed is decreasing, slowing down, velocity is increasing. If you are accelerating downward and speeding up, your velocity decreases. If you are slowing down, your velocity is getting closer to 0. Negative velocity is getting less negative is an increase. Acceleration is positive.
In this graph,
Mhm.
coming from minus 25 to minus 20.
Is that an increase or decrease? I didn't ask for magnitude. I didn't ask about speed. I asked about how does velocity change.
Still, I can tell you the direction, but
What is the direction? Tell me. Yes, but I don't ask about magnitude. I'm not asking for the speed change versus time. Never asking for the speed change versus time. Definition of acceleration is how does the velocity change over time. I do not ever take the absolute value for that. Please keep thinking about it. You were on the track to a big discovery, to a big insight, for something clicking, but keep pushing. Other questions? Keep them coming. Please. Negative velocities tell you that the direction of motion is downward. I mean, to be moving downward, aren't we subtracting off of our position? That's what negative velocity means. I'm subtracting off my position. Oh, very different. Yeah. It would start with a downward slope that is getting shallower. And if you start with a downward slope that's shallowing out, that's a positive curvature, positive acceleration too. But I find that harder to visualize. Yeah, please. Yes, I was. It was. Tension was greater than weight. if you are accelerating up. But direction of motion is not acceleration. Direction of motion is the sign of velocity, and you have to look at how does velocity change. This slowing down while moving down, that's a positive acceleration. Negative numbers getting less negative. I am adding to them to get them less negative. That's a positive upward acceleration. Forces up. I mean, you could do this experiment too, right? Take a 5-year-old, tie them to a rope, lower them slowly, and then bring them to rest. Actually, you could lower them as fast as you want. Just try not to let them hit the ground. Okay, lower them, then bring it to rest. Don't they feel heavier for a minute? That's the feeling of tension being bigger. You're bringing them to rest from moving downward. You are having to pull upward on them harder to stop their downward motion. Tension is bigger than weight. Acceleration is positive. Okay, I want to give one more conceptual. We've got 10 minutes. I want to give a conceptual thing that's not on the the slide here. Let's just identify forces. Let's talk about identifying forces. I've got a, what do I call this? Briefcase? Computer bag. I've got a bag, and I've got a little bag. Let's call this big and let's call this little, okay? Identify all the forces acting on little. Google form, put it in. Let me see that you can do this. Let me be precise. When we're doing this, I want you to identify force in 3 ways, 3 parts to it: the kind, the cause, the effect. That is to say, what kind of force from that list of 5, what is exerting that force, and what is feeling that force, okay? Tell me the fully specified force, all 3 parts, for every force acting on the bag, like this. I am supporting a big bag, which is supporting a little bag. I want you to identify all the forces acting on the little bag, but I want you to do so like we were talking about before. Don't just say gravity. Gravity is incorrect. You need to specify more precisely. 3 things to specify a force precisely: kind, thing causing force, thing feeling force. Kind, dealer, feeler. This is Google question J, by the way. Good, Jane. Good job. Good job, Jay Wisman. The big bad. I don't think this is Buffy. Good job, N. Blair. Okay, I'll give you a hint. There's more than one force. If there's just one force, you can't have a balance. Then they would have to accelerate. So hint, there's at least 2 forces. Oh my God. One more time, I'm asking you to specify the forces on the little bag. If you're telling me forces on me, that's not what I'm asking. Okay, so there are lots of things to learn from here. Let me put it that way. I want to go over wrong answers, and I want you to think about why they're wrong. And this is not just for the person who wrote the wrong answer. If you know something, you don't just know it's true because it's true. You should be able to explain why it's wrong. So I'm going to propose a wrong thing, turn to your neighbor, and argue about why it's wrong. Real fast. Tension force from the earth. Discuss with each other. Why is that not the forces acting on it? Okay, let's bring it together. The correct answer is there ain't no rope. There's no rope. There's no string. There's no chain. There's no cord. Okay, next thing to discuss real fast. Why is weight, comma, normal not an acceptable answer? Turn to each other, discuss. 30 seconds. Okay, time's up. Count them. Count them. Weight. Is that 3 words? No. Normal. Is that 3 words? No. What I said in the instructions are to name a force properly, you must name the kind, that person did correctly, the thing that exerts the force, and the thing that feels the force. So it is incorrect to say weight, comma, normal. The correct answer, by the way, as the next person put, weight from Earth on little and normal force from big on little. That is correct. There's more than one way to say that, but those are the 2 forces specified as I asked you to specify them. Next, wait, hold on, keep discussing, keep discussing. I have, here we go. Normal force, comma, weight force, comma, big bag touching small bag, comma, gravitational pull, comma, big bag feels weight force from small bag. Let's just focus on the last one. Why is big bag feels weight force from small bag impossible? Discuss with each other. Why is it impossible to say big bag feels weight force from small bag? Okay, let's bring it back. What do scales feel? What do scales measure? No. Yes. How hard you push on them. Look, hold a scale. Push it between your hands. Is it measuring your weight? Jump up and down on a scale. Is it measuring your weight? While your significant other is weighing themselves, put your toe on the scale. Is it measuring your weight? Their weight? No. Scales measure how hard you push on them. Weight is an interaction between a planet and an object. The weight force exists between the planet and this bag. This bag does not exert a weight force on the big bag. These 2 things, gravitational interaction is so small you can't even imagine. Theoretically, everything gravitates everything else, but that's not the kind of force. The big bag exerts a normal force on the little bag. We're out of time. I love you all. See you on Wednesday.